Swayam Prabha. Digital India. Educated India.
We have spent quite a bit of time on first order circuits, but we have also generalized some principles from there which will be applicable to higher order circuits. Now, everything that we said so far, with that you can analyze any circuits with a single capacitor or a single inductor. When I say single capacitor or inductor, it's assumed that you have done all the parallel series combinations possible with the source being null. Okay, with the source being null, you will effectively get a single capacitor or a single inductor. That is a first order circuit. Okay, so that all of that you can analyze now with what we have. Is that okay? There will be one time constant that you can find by finding the Thevenin resistance across the terminals of the capacitor or the inductor. Okay. Now, what we have not done so far is to put both inductors and capacitors together, right? So let's do that and see what happens. So far we had only resistors and inductors, or resistors and capacitors. Now we have everything together. Okay, now we have some current in the loop. The way I have chosen the circuit is to put all three elements in series. Of course, not necessary, we can have it in different ways. And we have a single loop with a loop current, and we have a number of variables: VR, VL, and VC. Okay, so first of all, please write down the differential equation. Terms of VC, please do that.
I will also derive the differential equation. You can compare your answer to what I get.
You do get a second order differential equation, which is
LC times second derivative of VC plus RC times time derivative of VC plus VC equals Vs.
okay. So you get that, and all you do is write KVL around this loop. VR plus VL plus VC equals Vs, and then express VR and VL in terms of VC. Okay, this is VR. C times dVc dt is the current, and that times R is the voltage across the resistor, and this L times derivative of that is the voltage across the inductor. Okay, so we can write the differential equation for the circuit in terms of VR or VL. What would it be in terms of VR? What would we get?
Again, please derive the differential equation in terms of VR and compare it to what I get.
You
will get exactly the same terms on the left hand side because the circuit is the same. LC times second derivative of VR with respect to time plus RC first derivative of VR with respect to time plus VR equals RC times first derivative of Vs, the source voltage. Okay.
Okay. As usual, you get the same homogeneous part of the equation. Okay. It's only the right hand side that is changed. And if you try it with VL, you will again get the exact same thing. That is, the left part is the same, the differential equation, and the right hand side will be different. Okay. So what it means, of course, is that the natural response will have the same form for any quantity in the circuit. And you can also write it in terms of I, which is also very easy. I is simply VR divided by R. Okay. So you just divide this by R and you will get the differential equation in terms of I. So this is the differential equation governing the circuit. Okay, and as usual, first we will find the natural response or the solution to the homogeneous equation. Okay, and what is that? What do you have to do? set Vs to 0. Okay. So we'll be left with
LC times second derivative of Vc with respect to time plus RC first derivative of Vc with respect to time plus Vc equals 0.
okay. And what is the form of the response you expect from this? Exponential. Okay, I mean that's the standard solution to any linear differential equation, right? That's simply because the derivative of an exponential is an exponential. So you sum up any number of derivatives together, you expect that all of them will have some exponential as a function of time. Okay, so the only way it will cancel is by having all the coefficients in the appropriate values. Okay, so if I do assume that Vc is something, let me use P times T here. Okay, and just for keeping dimensions correct, I will use V0, but that will cancel out anyway. So what do I have? What is the first term?
If I substitute this Vc into the differential equation,
Lc times P square plus Rc times P plus 1 times V0 exponential Pt equals 0. Okay. The only way this is going to happen is if that quadratic equation equals 0. I think you've done things of this type, right? This is known as the characteristic equation of the differential equation. When we did it for the first order circuit, we didn't do it directly like this. We manipulated the variables to get a homogeneous equation, and from there we got the answers. But exactly the same procedure will work, because what was the differential equation in that case?
Rc times first derivative of Vc plus Vc equals 0.
This was the homogeneous equation, and if I assume Vc is V0 exponential P times T, okay, I would get Rc times P plus 1 V0 exponential Pt equals 0. So values of P which satisfy this whole thing equals 0 will satisfy the differential equation, and obviously P is minus 1 by Rc. What are the dimensions of P? Frequency, right? Exponential Pt, the argument of the exponential should be dimensionless, so P times T is dimensionless, P is frequency. Okay, so if you solve the characteristic equation, you get possible frequencies of the exponential. Okay, so similarly here you have a quadratic equation, you will get two solutions. Okay, and what are the solutions? So this part has to be equal to 0. Okay. So there are two values of P. What are they?
We get the standard solution to the quadratic equation, which is minus Rc plus or minus square root of Rc squared minus 4 times Lc divided by 2 times Lc, which can also be written as minus R by 2L plus minus square root of R by 2L whole squared minus 1 by Lc.
Okay. So you can write it in either form. So there are two values of P that satisfy this. What does that mean for the natural response? there are two modes, two natural modes for the circuit. Okay, there is P1 and P2, and both are possible, exponential P1t and exponential P2t. And the actual natural response will be some linear combination of the two. Okay, because for a linear differential equation, if there are two possible solutions, any linear combination is also a solution. So in general, let's say A1 exponential P1t plus A2 exponential P2t, those are the solutions to this homogeneous differential equation. Okay, and how do you find A1 and A2? Initial condition. Okay. There are some conditions that we have to further check. Okay, so okay, now we have a quadratic equation. So what are the possibilities for the roots? So both P1 and P2 are real, in which case you simply get this two distinct exponentials. Okay, so that's the solution in that case, and you find A1 and A2 from initial conditions. And then it's possible that P1 and P2 are identical and real, and finally P1 and 2 are complex conjugates of each other. Okay, now you can also have P1 and 2 to be complex conjugates of each other. Okay, so when P1 and 2 are real and distinct, this is the natural response. Okay, and when does this happen? When will they be real and distinct? RC square greater than 4LC, or in other words, R square greater than 4L by C. Okay.
So in general, there will be two exponentials in the natural response. Now we have to consider two other cases as well, when P1 and P2 are real and identical, and when they are complex conjugates of each other. We will first, in another lesson, look at a second order system as a cascade of two first order systems and come back to these issues, because that will help us understand the solutions even better. Okay.